This is the second video on chapter 23, oblique asymptotes. And so we're going to look at part C of example 207. Part B was fairly basic, so I'm not making a video on part B. Part B, we didn't have any oblique asymptotes. We just had vertical and horizontal. But here we are going to have an oblique asymptote. What I didn't mention in the first video is how do you know if you have an oblique asymptote of a rational function? So when you have a polynomial divided by a polynomial, if this degree is exactly one more than this degree, you have an oblique asymptote. Okay? If you have a rational function, if the degree of the numerator is equal to the degree of the denominator, then you divide the lead coefficients, and that is your horizontal asymptote. If the degree of the numerator is strictly less than the degree of the denominator, then the horizontal line y equals 0 is a horizontal asymptote. But here, this degree is exactly one more than this degree, so we have an oblique asymptote. If the degrees differ by more than 1, then you have a polynomial that's what we call an asymptotic curve. So for example, if we change this 3 to a 4, then we would have a fourth degree divided by a second degree, and you would have a second degree polynomial, because the difference of 4 and 2 is 2, as your asymptotic curve. If this degree is 5, so if we change this to a 5 and kept this a 2, 5 minus 2 is 3, and then you would have a third degree polynomial as an asymptotic curve. But they're not called asymptotes because they're not lines. Okay, but here we have an oblique asymptote. Now, one thing I like to do with a rational function, any function really, is write it in as many useful ways as possible. So for this one, it means factoring the numerator and the denominator. We have an x plus 2 that's a factor of both the numerator and the denominator. So we can reduce it, and I have a not equal sign, because this function is not equal to this function. Why? This function is defined at -2. This one is not. However, that's a big difference in the two functions, but it's the only difference. So reducing this and studying the reduced form, looking at this reduced form, is easier than looking at the original function. We just have to always keep in mind they're not the same function. So they have a lot of the same properties, and so this is easier to work with, but we have to remember they're not quite the same. So we take this term, it is actually equal to this, which is equal to this. Why are we doing this? Well, again, we're looking for the oblique asymptote. So we're using the second technique that I showed you in the first video. We want x plus 1 to be a factor of something. Well, if we add a 3 here, then x squared plus 4x plus 3 factors as x plus 3 times x plus 1. So we're trying to get to here. So we add 3 because we want to. We subtract 3 because we have to. So why did we want to add 3? Again, so we could factor this term. But we had to subtract a -3 so we wouldn't, or we had to subtract 3 or add a -3 so we didn't change the function. So we rewrite the function this way. And this is equal to this because neither one of these functions is defined at -1. So we do preserve the equation here. But this helps us read the oblique asymptote. The oblique asymptote is now just y equals x plus 3. So that has slope 1 and y-intercept 3, and I put a 3, mark this 3, and then this -3 to draw this line. So that's our oblique asymptote. -1 is a factor in the denominator but not the numerator. That means we have a vertical asymptote at -1. So x equal to -1 is a vertical asymptote. Now remember, these two are not quite the same. This function's defined at -2, this one's not. But we want to know the limit. So we take the limit as x approaches -2 of g of x. Easiest way to do that is to substitute -2 in right here, and we have +4. So this graph has a hole at the point -2, +4. Because the limit as x approaches -2 of g of x is +4. But the function does not exist there because we're dividing by x plus 2. So this function's undefined at -2. But it does have a limit there. Remember, limits and function values are not necessarily the same. So we draw in our vertical asymptote, we drew in the oblique asymptote, we put the hole here at the point -2, +4. A couple other points that help us. 0 is a root in the numerator. So the point 0, 0 is on our graph. And -4 is a root in the numerator. So the point -4, 0 is on our graph. So we put this point here and this point here. They're helpful and they're easy to find. Also, another point that is helpful and easy to find is the y-intercept. So we substitute 0 in for x, but we already did that. If you substitute 0 in for x, you get 0. So here, our y-intercept is one of the x-intercepts as well. The limit as x approaches -1 from the right is -∞. And then we follow the oblique asymptote here. How do we know we're below the oblique asymptote? Because this function is x plus 3 minus something that's positive. And so the function is just a little bit below the line x plus 3 as x gets large. Over here, the limit as x approaches -1 from the left is infinity. And our function's a little bit above the line. Why? Because over here, x is negative. And so you substitute a negative x in here, you're subtracting a negative number that's positive, so we have x plus 3 plus something small. So we have our line plus something small, and so we're just adding a little bit. So our function is above the oblique asymptote over here.